In this presentation, we combine two chapters from the Watson text. Chapter 3 is on strategy and normal form, and Chapter 4 is on what we call mixed strategies. So these are related topics and fairly brief topics within the books. So we're going to combine them into one presentation. Let's discuss the normal or strategic form representation of a game. This is a description of strategy spaces and payoffs that helps to solve the game. It doesn't always tell you everything about the game, such as whether it's perfect or imperfect information, but it often tells you enough to effectively solve the game. For two-player games with finite strategy sets, the normal form can be written as a table or a decision matrix with appropriate labels. We will consider examples of games now in their normal form representation. And first of all, we're going to consider really the simplest class of games, the class that von Neumann and Morgenstern often focused on in their original treatise on game theory. These are zero-sum two-player games, kind of win-lose draw type games, or often win-lose draw type games. So these games are characterized by having two players, and the sum of the payoffs of the players, U1 plus U2, is always equal to 0, regardless of the particular outcome. The sum of payoffs always equals 0. So let's consider a two-player zero-sum game called evens and odds. In evens and odds, we each hold up either one or two fingers, so each of us meaning me and you playing against each other. We each hold up either one or two fingers. If the sum of fingers held up is even, then player 1, let's say you, wins. Otherwise, if the sum of fingers held up is odd, player 2, let's say me, wins. So I want there to be an odd sum of fingers, and you want there to be an even sum of fingers. This is kind of like a simplified version of paper, rock, scissors. The strategies available to you, player 1 in this game, cap S sub 1, are, well, you can hold up one finger or you can hold up two fingers. You only have one decision node, and at that decision node you can either hold up one or two fingers. Also, me, player 2, my capital S sub 2 set of strategies is I can hold up one finger or two fingers. So we have the same strategy set. Now, the set of strategy sets, cap S, or the set of strategy profiles, you can say, are that this is just the Cartesian product of my possible strategies and your possible strategies. Okay, so we can both hold up one finger. You can hold up one finger and I can hold up two fingers. You can hold up two fingers, I can hold up one finger, or we can both hold up two fingers. Those are the possible strategy profiles in the game, and each leads to a different outcome, or each leads to one of the possible outcomes. So here is evens odds in extensive form and then in normal form. Okay, and we know that this is a game of imperfect information because in extensive form we have a dashed line between player 2's two decision nodes, meaning that when player 2 moves, player 2 does not know whether player 1 will hold up one finger or two. Okay, so I'm player 2, so I don't know whether you'll hold up one finger or two fingers when I decide whether to hold up one finger or two fingers, because we make the decision at the same time. The game would be easy if I knew what you were going to do. So as player 2, I'm going for odds. So if I knew you were going to hold up one finger, then I would just hold up two fingers. Okay? And then we would follow the path along the tree diagram where you player 1 holds up one finger, I hold up two fingers, you lose a point, and I win a point. Okay? And if I knew you were going to hold up two fingers as player 2, then I would hold up one finger. Because if we follow the path along the tree diagram where you hold up two fingers, then I hold up one finger, then I would win one, you would lose one. So you would lose one as player 1, I would win one as player 2. But as it is, it's simultaneous move, so we have the dashed line, and it's imperfectly informed, so I don't know what you're going to do, so I have to keep guessing, and so do you. We also see this game in normal or strategic form. In normal or strategic form, we have player one on the vertical. Okay, so player one, we see on the vertical margin, they make a decision vertically between holding up one finger and holding up two fingers. If player one holds up one finger, then they put the game in the topmost row of cells. Okay, so this is often called the row player. They decide which row the outcome of the game lands in. So if player one chooses to hold up one finger, they put the game up or in the topmost row. If player one chooses two fingers, they put the game down or in the bottommost row. Player two is moving horizontally to choose a strategy between one finger and two fingers. And player two is called the column player because they decide whether the game goes in the leftmost column when they choose one finger or the rightmost column when they choose two fingers. So player one, which is you in this case, is choosing between one finger and two finger. So they're choosing which row the game lands in. And they're doing so to maximize their payoff, which is always listed in as the first entry in a cell. So in each cell there are payoffs or outcomes. And the first listed payoff is for player one, the row player. The second listed is for player two, the column player. So your goal in this game is to, based on your beliefs about what I might do, to choose one finger or two fingers, so to put the game in a row that you feel will maximize your payoff, which is, as player one, the first payoff in the cell. And my goal as player two is to choose horizontally, so to put the game in the column that, based on my beliefs on what you will do, I feel maximizes my payoff as player two, which my payoff is always listed as the second entry or the second payoff in a given cell. So let us discuss another game that is imperfectly informed, for which there is imperfect information, and we will discuss the characteristics of this game and show it in extensive form. However, we will solve it in normal form. As I said earlier, it's often easiest to solve games of imperfect information in the normal form or using the game matrix. Whether or not you solve a game in extensive form, it's often helpful to see it in extensive form or to draw it in extensive form to understand the structure and elements of the game. Okay, so the game we're going to consider is called Battle of the Networks. It is a constant sum game. In general, we say that a game is constant sum if the payoffs always add up to the same value, some constant k. In this case, it is a 100 sum game. Payoffs always add up to 100 because this is Battle of the Networks, and so TV networks fight over a total market share of 100 or 100% of the market. Okay, in this game, two networks simultaneously choose whether they want to program a sitcom or sports during some primetime slot. And so this is imperfect information. We see a dashed line between the two decision nodes of player two. Okay, and we also see that if we see the payoff, so we see if both choose sitcom, then it seems network one is better at sitcoms and they'll get most of the market share. If both choose sports, then network two is better at sports. And then if they do something heterogeneous, then network one chooses sitcom, network two chooses sports, then apparently most people like sitcoms. So network one would get most of the share, most of the market, or at least most of the market likes sitcoms on network one, it seems. Okay, so that's the game. We're going to solve it in normal form, but that's the extensive form of the game. This is the normal or strategic form for Battle of the Networks. It includes a role player, network 1, or player 1. So this player decides vertically which type of programming to choose, sitcom or sports. And then network 2 chooses horizontally between sitcom and sports. And remember that network 1 or player 1 considers first payouts, network 2 considers second payouts. So for example, if both networks choose sitcom, then the outcome is described by the top left cell. And what the top left cell is telling us is that in that outcome, network 1 would get 55% of the market share, and network 2 would get 45% of the market share. So I want to preview how we would go about solving a game like Battle of the Networks, how we would solve a game using its normal form. So we know that the Nash equilibrium of a finite move game involves a consideration of each player's response to each other player's set of possible moves. Okay, so given some belief on what the other player will do, the player who's evaluating should know their best response to that belief on the other player's actions. In a two-player game with two strategies per player, let's say each player could do A or B, we can solve the game simply by doing the following. If player 1, the role player, believes that player 2 will do A, should player 1 do A or B? So we ask that question. If player 1 believes that player 2 will do B, should player 1 do A or B? So we ask this if-then type of question. And then, so we've kind of evaluated the possibilities. We've evaluated what player 1 should do given each possible belief on player 2. Then we flip it and we evaluate what player 2 should do given possible beliefs on what player 1 will do. So if player 2, the column player, believes that player 1 will do A, should player 2 do A or B, which will make player 2 better off? If player 2 believes that player 1 will do B, should player 2 do A or B, which will leave player 2 better off? Okay, so this will lead us to the solution or the Nash equilibrium of the game if we follow this line of thinking. The Nash equilibrium of a game occurs where each player has responded best to the other players. It is a stable point. If I am in a best response and you are in a best response, there is no impetus to deviate from this set of strategies. The stable point is found by conducting strategic if-then analysis for each player. So a Nash equilibrium is nothing more than a set of best responses, or a condition under which, a state under which each player is in best response to the other players. So let us begin our best response analysis or Nash equilibrium analysis for the Battle of the Networks game. And let's begin by considering what player 1 will do given possible beliefs on player 2's actions. Well, if player 1, so let's think of the row player who's thinking vertically and about first payoffs, believes that player 2 will choose sitcom, that is, that player 2 will put the game in the first column, then there are two possible outcomes for player 1. Player 1 can get a payoff of 55 by choosing sitcom, or player 1 can get a payoff of 50 by choosing sports programming. Player 1 chooses sitcom under this belief because 55 is greater than 50. In the sitcom column, we draw an arrow up to signify that player 1 will choose sitcom as a best response to player 2 choosing sitcom. So just to summarize, if player 2 chooses sitcom, or if player 1 believes that player 2 will choose sitcom, then because 55 is greater than 50, player 1 will choose sitcom in this case. We say that sitcom by player 1 is a best response to the belief that player 2 will choose sitcom. So, or you could say if player 2 chooses sitcom, then player 1's best response is to choose sitcom. If player 1, again the role player, who thinks vertically and about first payoffs, believes that player 2 will choose sports programming, that is, that player 2 will put the game in the second column, then player 1 can get a payoff of 52 by choosing sitcom and a payoff of 45 by choosing sports programming. Player 1, under this belief, chooses sitcom in this case as well. In the sports column, we draw an arrow up to signify that player 1 will choose sitcom as a best response to player 2 choosing sports programming. Therefore, player 1's set of vertical best response arrows appear as follows. Both of player 1's best response arrows point in the same direction. Regardless of player 1's belief about player 2's strategy, player 1's best response is to choose sitcom in this case. In such cases, which don't occur in every game, but in cases where arrows for a player are all pointing in the same direction, we call the strategy, in this case sitcom, the always chosen strategy, a dominant strategy for player 1. Dominant strategies are a best response to any possible strategy of the other players. It is a no-brainer to play a dominant strategy because it always leaves you best off, regardless of what the other player does. We will see that it is straightforward to solve for equilibrium in games that feature dominant strategies for each player. Just play your dominant strategy. Let us now consider the column players, or player 2's best response analysis. If player 2, or the column player, who thinks horizontally and about second payoffs, believes that player 1 will choose sitcom programming, that is, player 1 will put the game in the first row, then player 2 can get a payoff of 45 by choosing sitcom, or can get a payoff of 48 by choosing sports programming. Player 2 chooses sports under this belief. In the sitcom row, then, we draw an arrow right to signify that player 2 will choose sports as a best response to player 1 choosing sitcom. So just to summarize, if player 1 chooses sitcom, or if player 2 believes that player 1 will choose sitcom, then 48 is greater than 45. Player 2 chooses sports in this case. Sports by player 2 is a best response to the belief that player 1 will choose sitcom. If player 2, or the column player who thinks horizontally and about second payoffs, believes that player 1 will choose sports, that is, that player 1 will put the game in the second row, then player 2 can get a payoff of 50 by choosing sitcom, or a payoff of 55 by choosing sports programming. Player 2 chooses sports under this belief because 55 is greater than 50. In the sports row, we draw an arrow right to signify that player 2 will choose sports as a best response to player 1 choosing sports. So to summarize, if player 1 chooses sports, then 55 is greater than 50, so player 2 chooses sports in this case. Sports by player 2 is a best response to the belief that player 1 will choose sports. So player 2's set of horizontal best response arrows appear as follows. Both of player 2's best response arrows point in the same direction to the right, or towards sports. Regardless of player 2's belief about player 1's strategy, player 2's best response is to always choose sports. In this case, we call sports a dominant strategy for player 2. So here is a complete best response analysis for the game where the vertical arrows constitute best response analysis done by player 1 or network 1 for this Battle of the Networks game. And horizontal arrows, those moving laterally, represent best response analysis by player 2. Okay, so as we said earlier, both players have what we call a dominant strategy in this game. So for player 1, the dominant strategy is to play sitcom. Okay, so that is to say, if player 1 believes that player 2 will choose sitcom, then player 1 should choose sitcom. If player 1 believes player 2 will choose sports, player 1 should still choose sitcom. Okay, so that's why each of those arrows representing best response analysis for player 1 are upward moving arrows. For player 2, we have horizontal arrows. Player 2 also has a dominant strategy of programming sports during this primetime slot. And so that first or topmost arrow to the right suggests that if player 2 believes player 1 will choose sitcom, then player 2 should choose sports because 48 is greater than 45. The bottommost horizontal arrow suggests that if player 2 believes player 1 will choose sports, then player 2 should choose sports because 55 is greater than 50. Okay? A Nash equilibrium, then, is a stable set of strategies in a game. In the normal form of games with finite number of moves, this means that all arrows are pointed toward a given cell, i.e., it is a mutual best response such that no player has incentive to unilaterally deviate from that equilibrium or that set of strategies. In this case, all arrows are pointed to the cell sitcom sports. This is a Nash equilibrium. The Nash equilibrium is network 1 chooses sitcom, network 2 chooses sports. And we obtained that through best response analysis. We did our arrows, we did our best response analysis for given beliefs about what the other player would do, and then we just found where arrows met. We found the cell in which arrows met, and we reported the strategies that are represented by that cell. The Nash equilibrium outcome in this game is the payoff pair 52-48. That is, player 1's payoff is 52 and player 2's payoff is 48. So an equilibrium is a set of strategies. An equilibrium outcome is an ordered set of payoffs for each player. Now we will discuss mixed strategies, the topic of Chapter 4. Well, what are mixed strategies? In some games, predictability is fatal. Okay, so if you're a baseball pitcher, you don't want to pitch the same pitch at the same speed every time. So in these cases, one mixes among strategies. And so we have to introduce a notation for mixed strategies in this game. And so we have this term delta capital S sub I. This is the set of probability distributions over player I's strategy set. So these are all of the possible mixings that a player can do. You can think of a game between, in baseball, a pitcher and a batter. Okay, so the pitcher has a set of probability distributions over which he or she can choose between pitches. Let's say the pitcher has a fastball and a breaking ball. Okay, one possibility is that the pitcher could throw fastball 80% of the time, breaking 20% of the time. That's one possible probability distribution over player I's strategy set. Alternatively, player I could choose fastball 70% of the time, breaking ball 30% of the time, or fastball 60% of the time, breaking ball 40% of the time. These are all possible probability distributions over the pitcher's strategy set. Okay, and analogously, the batter has to anticipate, has to kind of time the fastball. So the batter has to choose a mixed strategy. So the batter can't always time for fastball. So the batter might be timing for fastball 80% of the time, timing for breaking ball 20% of the time, or timing for fastball 70% of the time, timing for breaking ball 30% of the time, etc., etc. So all of these are possible probability distributions over, we could say, player J or the batter's strategy set. Okay, so delta, capital S sub I, is the set of possible probability distributions that can be chosen. So an example of a mixed strategy is, well, a pitcher might choose to pitch fastball 80% of the time, slider 20% of the time. And an implication here is that the pitcher who does this is randomly mixing between fastball and slider. Okay, so the pitcher is not only following this probability distribution of pitching fastball 4/5 of the time, slider 1/5 of the time, but is doing so in a random or non-patterned way. If a pitcher follows this probability distribution but does so in a patterned way, such as fastball, 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 slider, fastball, 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 slider, there's no mystery here, and the batter will know every time which pitch to time for. Okay, so it's not only following a probability distribution, but also doing so in a random or unpatterned manner. So then delta cap S sub I is all possible mixed strategy distributions that a player could choose. And then theta sub I, which is an element of delta cap S sub I, is a belief by another player about player I's strategy choice. So you have a strategy choice, and then you have a belief about that strategy choice. So in this case, the pitcher is making the strategy choice, and then the batter's having some belief about this strategy choice. And a single mixed strategy chosen by player I, we call sigma sub I. It's just an element of the possible mixed strategy distributions. So the example above gives a possible sigma sub I, one possible mixed strategy that the player may choose.